Perfect. All right. Well, as Tracy mentioned, I'm Bethany Seibert. I'm the product manager for the dedicated outdoor air systems group here at Greenhack. I'm located in central Wisconsin and have been a part of the Greenhack group for just over 7 years, and actually mainly focused in energy recovery, dedicated outdoor air systems as well. So what we're covering today are a lot of regulation changes that are going to be affecting really your rooftop equipment for your partial recirc type applications, and how these changes in regulations are going to introduce different technologies, different schematic sequences in your cooling package DX systems to be able to meet or exceed these higher efficiency changes. So we'll definitely cover a lot of that and really why different technologies can give you benefits versus the others, and then get into some other regulation changes that are coming in the future, just to give you some updates on things you might be hearing around refrigerant changes, and also regulations coming for DX DOAS equipment as well. And then finally covering a few pieces of new things coming from our group from Greenhack. So to get started, just on these DOE regulation updates that are coming in 2023, it's really important to understand where these regulations are coming from. So when we look at commercial rooftop equipment, it really starts with ASHRAE 340-360 standard. And that is a standard that rooftop manufacturers need to test to provide efficiency values required in the market. And these efficiency values that are regulated by the Department of Energy is the IEER value, which is an integrated energy efficiency rating. And that test process is followed through that 340-360. And in turn, we have to ensure that we meet minimums provided by the Department of Energy, because they're concerned of overall energy consumption and reducing that energy consumption, obviously, each and every year to try and reduce that. And how they can allow energy reduction is by increasing these minimum efficiencies. So I'm just going to walk through what IEER is, so everyone's on the same page, and how that calculation is provided. So IEER is that integrated energy efficiency ratio, as I mentioned, and it's actually a weighted calculation. So it's looking at your efficiency of that equipment in several different conditions, not just at your peak load like an EER would, right? So IEER is actually looking at 4 different weighted conditions. So these weights are really based on weather bin data throughout the entire US, and basically stating at these conditions, this percentage of the year you may see in this condition. At this next condition, here's another weight of that condition. That would be a part of this full calculation. The one important thing to note here is IEER is very specific to your rooftop style type of equipment or your partial recirc application. So as I mentioned, there are additional regulations and efficiency metrics for dedicated outdoor air systems that are going to be different than IEER, and we'll cover that a little bit later as well. When we talk about the equation for calculating IEER, this is really what it looks like. It's looking at those different weights of these 4 points and calculating an EER at each of those given conditions, and then weighting those and coming up with this full IEER value. So we look at the 4 different points. It's really important to understand where these are actually being tested to, because in many circumstances, we're designing equipment for your full load day, right? You're making sure you have enough cooling dehumidification for that absolute full load day. And then majority of the time, we're in a part load condition. So we still need to make sure we're efficient in those cases as well. And that's what the IEER is really coming into play. So you can see point A is a 2% of the weight of the calculation, and that's tested at full capacity. So just as I said, that condition is not majority of the time. In this weight, it's 2% of the total calculation, and that's at a 95-degree ambient. Point B and C are probably your most part load and are definitely the heaviest weighted in this calculation. So point B is actually at 62% of the weight of the calculation. And that is tested at 75% of the full capacity and at an 81.5-degree ambient. C is the second highest weighted. Now you're at 50% capacity and at a 68-degree ambient. And then point D for these cooling efficiencies is 13% weight and is at 25% at that 65 degrees. And really below that, you may start getting into an economizer state, right? Below 65 degrees. So the important piece to note here is IEER is heavily weighted to 98% part load. So significant to a part load condition versus that peak load. So how do you achieve these higher increases then that the DOE is now regulating starting in 2023? Well, it's important to understand though how much it's changing to know what might change in this type of equipment. So when we look at what the Department of Energy is making changes to, on average, you're going to see at different capacities a change anywhere from about 15 to 20% increase in efficiency ratings. So quite a big bump compared to where they were in 2018, and they've taken quite a big bump in 2018 as well. So there's been a lot of work that the Department of Energy has done, and obviously manufacturers are doing to help increase the energy efficiency of this type of equipment. So in this example here, this is looking at small commercial package units that are anywhere from about 5 to just under 12 tons of capacity. And you can see the rating changes here. In this capacity range, the increase is about 15 to 16% in energy efficiency ratio. Looking at the next capacity range that is increasing, this capacity range is now up to about 20 tons, your large commercial package, and you can see the increase here is about 15 to 17%. And then if we go to our very large commercial package, now you're looking at units up to about 63 tons of capacity. These range from increasing from anywhere from 14 to 18% as far as an IEER metric from 2018 to 2023. So quite a bit of an increase in the 5 to about 60 to 65 ton range when it comes to these energy efficiency ratios. Now, what does that mean? How are we as manufacturers able to increase our efficiencies to meet these minimums, if not exceed them? Well, it really is quite a bit of a game changer in the different technologies or different system design that you have on your refrigeration system. Say in many cases, when I say standard design won't meet these new minimums, it's taking all of those top technologies or schematics of a system and standardizing those, as that's how it's typically been designed in the past with digital scroll compressors, fin and tube coils, AC on-off condenser fans. And then typically even at your lower, even lower capacities, a dual circuit design where you have more than one compressor and more than one circuit. Now, when we look at how are we able to achieve these higher efficiencies, there's definitely going to be technologies that you've already seen in the market, but are going to become more predominant. And in many cases, some of these at the top would become obsolete. And any combination of these can help you achieve different efficiency metrics. So for example, inverter compressors. This is a technology that's been around quite a bit in the last few years and become very common. So you may have seen this very commonly already, although digital compressors are still being utilized today, right? Microchannel coils. This technology has definitely been phased in over the past, I would say, decade, and really pronounced in the market today when it comes to your higher value rooftop type equipment. In addition to that, EC condenser fans for head pressure control provides efficiency when you're in those part low conditions. It has a lot of other benefits as well from a sound perspective, reheat capacity, definitely becoming more predominant in the market. And then one that you'll see more often, and we'll discuss a little bit further in detail today, is dual circuit going to more of a single circuit design at even higher capacities than what you may see today. So we'll go through all the benefits that each of these can help provide and really focus in on certain areas and how those can increase your efficiency metrics and include some examples here for you today. So the first one's compressors. If you all are familiar with how these technologies work, this is just a quick review of the differences between them. Digital scroll, here's a great animation where you're going to show the scrolls engage and disengage, or the compressor loading and unloading based on demand. The big thing to note here from an efficiency standpoint is even when you're in an unloaded or a disengaged state, that scroll is still operating. You're still providing power to that compressor. So your efficiency isn't as great, although your modulation control is a great benefit for a digital. Inverter compressor, the benefit here is huge on efficiency. Your VFD is going to change speed based on the demand of the system. And now we're going to speed up or slow down that interior scroll and reduce the power consumption coming from that compressor. So when we look at the differences between the two, how does this change from an efficiency standpoint as these compressors speed up or slow down? Or I should say how the capacity changes based on the demand and the efficiency effects from that. So we can look at that through this chart here that really shows the difference in your energy efficiency ratio between an inverter and digital compressor. So y-axis, we're showing EER, and x-axis, we're showing that compressor speed, which is really based on the demand of the system, right? The yellow line is showing the digital compressor EER, and the blue line is showing an inverter compressor EER. So just as we showed in the last slide, where you're able to see how the digital compressor loads and unloads, but again, that scroll is still rotating and still utilizing power. You can see that yellow line as the compressor speed or demand starts to go down, the demand on that compressor. So now you're in more of a disengaged state. You're starting to utilize some reduction in power, but it's not significant because again, you're still rotating that scroll and still providing power to that compressor. Versus the inverter compressor actually becomes more efficient as you slow down that compressor or the demand capacity on that compressor starts to reduce because we're able to reduce the power consumption through that VFD. So this slide is really powerful in the effects of how an inverter can be so much more efficient in those part load conditions, which again, what the Department of Energy is regulating is IEER, and 98% of that is weighted to part load. So this is why you're seeing a huge movement to inverter compressor versus digital. And in many cases, you're going to see manufacturers either phase digital out and just focus on inverter compressor because of the huge advantage you see here. Now, the other technology I shared on the previous slide that many manufacturers are gravitating towards are EC condenser fans. So it's important to understand condenser fan energy and how it's utilized in the entire refrigeration system. So when we look at a schematic of a refrigeration system, the big points here are you obviously have your compressors. This is showing actually a dual circuit with an interlace coil. So you're going to see your compressors over here on the left, condensing section. So your condenser coil here, this is an interlaced coil. And then you can see here your evaporative coil, which again is an interlaced coil. In a situation like this, your condenser fans exist to maintain head pressure control while your compressors are modulating or staging on and off. So we will be rejecting heat out of the system through the condenser fan section based on the demand of the compressors. So what's important to note here is that when these compressors run, the condenser needs proper airflow across this coil to maintain that, to reject enough heat out of the system. And when you have more than one circuit, this also comes into play into how far you can speed up or slow down your condenser fans. So in this example, when we showed a dual circuit, so we showed two compressors, but an interlaced coil on this condenser section. Here you're showing a circuit A in this interlaced coil and a circuit B. This entire coil face while you may have one compressor running in a part low condition, this entire coil face will still need proper airflow across it. So with interlaced coils, which is very common, especially at lower capacities and from a cost benefit as well, you're going to still have to operate your condenser fans here at higher speeds, even if, let's say, circuit B isn't in operation in a part low condition. Circuit A still covers the full face of the coil, right? So we still need to operate these condenser fans at higher speeds to get that proper airflow to maintain head pressure control. So these are some things to keep in mind when you think about the different circuiting as well, which was another point that I had on the slide. Condenser fans moving to modulation helps in these cases, and then also the difference in circuiting. I'll go through an example here to really hone in on how circuiting, going from dual circuit to single circuit, can improve efficiency, as well as the inverter and modulating condenser fans can really provide a huge efficiency benefit. So we're going to actually focus on a 15-ton system and go through the energy savings at these different points that are being rated by the Department of Energy. So here's an example of a single circuit versus a dual circuit. So if you look on the left, we're showing a dual circuit 15-ton system. Important things to keep in mind here is that we're looking at comparing a dual circuit inverter on the lead circuit with a stage compressor on-off compressor on the leg circuit. And then we're going to compare that to a single circuit 15-ton inverter. So inverters on both, but we're comparing dual to single in this example. This example as well is going to have lead EC condenser fan on both the dual circuit and the single circuit, and then the additional leg circuits will have stage condensing fans. Some things to note when you're looking at this with the dual circuit, obviously each of the compressors account for 50% of the system. So that it's important to note that when you're looking at the power consumption of each is going to definitely change because you have the dual circuit versus the single, with the difference in the circuiting here. So if we look at just point A, for example, full load, not really much of a difference from an EER perspective. Again, this goes into your calculation for how you're calculating your IEER. And again, this is only 2% of the weight of the calculation, so very minimal. But you can see EER pretty much the exact same between the dual circuit and single circuit in this 15-ton example. Where things really start to change, though, is in these part low conditions. So in this example, when we get to point B, which is 62% of the weight, we're at a 75% capacity. You can see here that in the dual circuit, we would have our stage compressor on. So we're utilizing full power of that stage compressor. And then your inverter compressor speed is at about 40% to achieve that capacity. So in this case, your inverter is modulating, plus you have your stage compressor on. When you compare that to the single circuit, now you're able to modulate that inverter compressor to about 68%. And this is going to have a significant kilowatt power reduction by being able to have one single compressor modulated down versus having a stage compressor on and then an inverter modulated, just as you saw on that graph previously. In addition to that, because of having a single circuit, we can significantly modulate that EC condenser fan down in this part low condition. So you can see it's modulated down to 42% versus in the dual circuit, that is shown at 72%. Because again, that's an interlaced coil. And even though we've modulated down on our A circuit here, we can't modulate it down significantly lower because we need to have proper airflow through that condenser coil because we do have circuit B on at full capacity. So in this case, you can see at the bottom, the differences between the EER calculation, that'll be a part of that point B weighted weight. So 17 versus 14.9. As we keep looking at the different points in the IEER calculation. Point C now is 24% of that weight, and now we're at 50% capacity. Now we start seeing huge changes in your EER values, and you can see that in the diagram showcasing the difference between these two systems. So in this case, the dual circuit is going to have that inverter compressor probably on at 100%, or it's going to be modulating between that and the stage compressor coming on and the inverter coming on at a minimum capacity. So at this point, to try and meet 50% capacity, you're probably going to be seeing some combination of that, which obviously is going to be exerting more power. But not only that, it's going to have a sound implication as well from that stage compressor coming on and off in this particular example. In addition to that, you're going to see on the single circuit, you're going to be able to significantly modulate the speed of that inverter compressor down. And then your condenser fans, you're actually able to turn off your stage condensing fans and just utilize that EC condenser fan and modulate that down as well. Versus on the dual circuit, again, you're operating one of those compressors at full speed. So we're not able to modulate down as far and still have to have those stage condenser fans on with that interlaced coil design. So 25.2 EER on a single circuit at point C and 14 EER for the dual circuit on this 15-ton. And then if we look at point D, so this is going to be at 25% capacity, and this is 12% of the weight of the IEER calculation. Again, you're going to see huge benefits of the single circuit in these part load conditions. Remember, 65 degrees, 68 degrees, 81.5 are points B, C, and D, ambient conditions. So definitely conditions you would see in your part load days. Here, you're going to notice the difference here is the inverter compressor is at about 45%, and the 15-ton single circuit is at about 21%. So we're able to modulate that one significantly down further. Again, being able to modulate that inverter compressor down increases the efficiency, as we showed on that graph prior, versus the dual circuit. That's only 50% of the system, that inverter is, and it's only able to modulate down to 45% at that point. Similar fashion with the condensing fans. Now we've had our stage condensing fans off in both scenarios. However, again, the EC condenser fan is able to modulate down further in the single circuit versus a dual circuit, providing that big change in EER at point D. So you can see 37.6 versus 23.8. So when we calculate this all out, pulled this equation back in each of the IEERs or the EERs for the IEER value in, we get an IEER for a single circuit design at 18.8 in this example versus a dual circuit at 14.2. So this may be on the ragged edge of what is acceptable depending on what additional components you have in your system, because obviously you have other components within the system drawing power, although majority is from the compressors, condenser fans, right? But in this case, depending on your heating downstream, things like that, that could change your IEER value to not meet the new efficiency ratings. So this example was to highlight the benefits of the inverter and having a single circuit at higher capacities, as well as how it's able to help you with your condenser fan modulation and how that improves efficiency as well. So huge efficiency gains from having that single circuit with inverter compressor, lead EC condenser fan. In this example, at even higher tonnages that maybe you have seen in the past. Another benefit of going from dual circuit to single circuit is you're going to greatly increase your reheat capacity. So what we're showing here on the left is the same dual circuit 15-ton example. However, we've just broken out the circuits here separately to really hone in on the fact that typically in design, you're going to see one of the circuits have reheat and the other circuit not have the reheat coil. So in this example here, it's showing that circuit A has the reheat. You could have it in, and manufacturers do this for different reasons. You could have the reheat on circuit B too. The point here is circuit A has reheat on it. However, that's only half the capacity of the entire system. So you will only ever be able to utilize half of the heat generated in the entire refrigeration system for reheat in a dual circuit design. Whereas single circuit, now at this higher capacity, you're able to utilize the entire capacity generated in that entire system for reheat if need be. And this is going to especially help you on a part load day. So really in a dual circuit, reheat is on one circuit again, typically providing half the reheat capacity available in that entire system. So what does this mean in certain part load conditions? We can walk through an example of this one as well and really allow you to see the difference in reheat capacity as you start going into different part load conditions between dual and single circuit. So here we're showing different ambient conditions. This was for a 15-ton 2000 CFM unit, outdoor rooftop. Ambient conditions were at 9578, probably pretty close to your full design day. And now we're looking at an inverter and standard scroll compressor in a dual circuit again, right? And then an inverter scroll single circuit in this example. You can see we're listing reheat leaving air temperatures. So at this ambient condition, there's lots of heat generated in the refrigeration system. So we're able to utilize that even in a dual circuit to hit an 80-degree leaving air temperature because now we're at a full load. Inverter compressor, same thing. We're able to achieve a higher leaving air temperature because we're at full load. Now, when we start going down into our part load, that's where we're going to start seeing the reduction in reheat capacity in that dual circuit. So here's an example of a part load day, 80-degree dry bulb, 73-degree wet bulb. In this condition, you're going to start seeing a reduction in reheat to the point where you're going to be below a 70-degree leaving air temperature. And then if we go even further, maybe a 72 dry bulb, 69 wet bulb, maybe it's I guess in Georgia, maybe that would be considered cooler. That would be a warmer day for us, but high humidity, maybe you're getting to a point where you maybe have a rainy day in the summer or springtime, and you're going to struggle to meet reheat capacity because you only are able to utilize the reheat on one of the circuits, and that's half the capacity of the entire system. So the important thing here again, we talk about part load with single circuit versus dual. Remember, 98% of the weighted condition for IEER is in part load conditions. And here we're showing part load conditions. So there's a reason why there's a significant weight to part load in the IEER calculations, because majority of the year is in those conditions. So making sure that you have enough reheat capacity on part load will help you in a single circuit design at higher capacities as well. The other thing to note is for that single circuit inverter, we can continue to slow down that EC condenser fan. We showed it in the example before, point C, where we were able to stage off our staged condenser fans and just modulate that EC, versus the dual circuit, we are actually, some of that heat we could have saved for the reheat coil is having to be rejected out of the condenser fans in this case, so that we have proper airflow across that coil. So again, that's able to help you. Reheat capacity is able to be increased in a single circuit design. So we went through quite a bit of the advantages of single circuit. What are some drawbacks, and why obviously have we continued to use dual circuit today, right? Some of the drawbacks that some people may be pointing out is for single circuit versus dual, your turn down might not be as great, right? Well, if you still look at that 15-ton example, that compressor at point D, which was at the 65-degree ambient, was modulated down to 21%. So we're still able to achieve a 50 to 55-degree leaving air temperature off of our coil, and obviously reheat after that and have the turn down to be able to achieve that for our point D. So you're still able to get down to 15 to 20% modulation control, whereas maybe obviously with a dual circuit can go lower. But you could see by that example, that point D was at 21% turn down and able to achieve the 50 to 55 degree, which at that point, you may be beyond that point, you would likely start going into an economizer state anyways. The other drawback some people might be pointing out is redundancy. They like having more than one circuit, so that if you get into a situation where, let's say, compressor A fails on a dual circuit, that compressor B circuit can still limp along and keep you going, even though you still may not be meeting the condition in the space and still have complaints at that point. Some people may say they like having that redundancy. It depends on what type of system you have. If you have two compressors in tandem on a single circuit, that obviously would contaminate that system at that point. But from a redundancy standpoint, to really look at why you're doing that, it's really looking at compressor failure. So you're ensuring that if a compressor fails, you're able to have one of those circuits again limp along. But one thing to look at though is how often are compressors failing that we would stick to dual circuit versus single circuit when there's all these advantages over here for single circuit. So from a redundancy standpoint, we looked at the last 5 years of compressor failures, and we have less than a 2% failure rate on compressors. So it's a very, very low, the compressor failure rate, where you're getting huge advantages for energy savings, increased reheat capacity and not having to worry about that at part load, and huge benefits from sound as well from having that single circuit and not having condenser fans ramped up as high and having stage compressors coming on and off. There's huge advantages for all of your part load conditions, energy efficiency here versus trying to compensate for less than 2% of that time where you could run into a scenario of a compressor failure. So lots of benefits here for a single circuit versus a dual circuit design. Okay, what other design options can improve efficiencies? Obviously, we went through the examples here of single circuit inverter compressors, lead EC condenser fan. Another one would be to go to all EC condenser fans versus lead EC. So in those cases, you get even more energy efficiency savings by modulating all of your condenser fans down, and then obviously staging those off as your head pressure modulates based on the system demand. That can help improve them. Also adds cost though, right? Another option would be a phase split condensing coil. So when we looked at earlier the dual circuit design, very commonly you're going to see interlaced coils where those two coils are going to have the interlaced circuits. You could look at a split coil where you have split sections of a coil, and now you have condenser fans specific to those split coil sections. It becomes a lot more complex from a control standpoint and a lot more costly at lower tonnages and being able to fit the right size coil there. And it still limits your reheat capacity. So you do not avoid it in that case, unless you were to put reheat on both circuits. So again, it would add more cost in that situation as well. Other design options you might see in the market, you may see a digital compressor with a 2-stage compressor on the leg circuit. That example can in many cases meet the very, very minimum, but it's much lower than the industry standard. So when you saw the 18.8 for that 15-ton, that's very common for many of the very predominant manufacturers in the market to have those much higher efficiencies in that 18 to 20 IEER range. Digital with a 2-stage compressor can still in some cases meet the bare minimum here that's being laid out for 2023, but you're still going to have the increased sound from a digital loading and unloading, and also the two-stage coming on and off. It becomes a lot more complex from a control standpoint as well, now that you have to utilize a two-stage versus an on-off compressor. And again, this would still be a dual circuit design, so you'd still have those limits in reheat capacity and obviously reduced efficiency gains. And then one other one that I wanted to point out here is tandem compressors in a single circuit. You're definitely going to see tandems in a single circuit being utilized because inverter compressor sizing only goes up so large for a single compressor. So that can allow you to improve your efficiencies as well, as we pointed out, the single circuit benefits, and then having more than one compressor on a circuit, on that circuit. So these are just another, I guess I would say, high level ones that you might see out in the market as well to be able to improve efficiencies, but maybe some drawbacks that you might have with those as well. All right, so what else is coming from regulation? That really covered the efficiency changes coming from the DOE as far as rooftop type applications for your partial recirc and what changes you might see in equipment. Again, a lot of those you've seen already. You've seen a lot of the changes in manufacturers providing inverter compressors, lead EC condenser fans, or all EC condenser fans. And then you definitely have or are going to start seeing more of that single circuit design at higher capacities as well to meet those efficiencies. But what else is coming from regulations? So I mentioned before that the DOE is looking to regulate DOAS equipment as well. So 100% outside air equipment is actually measured to an ISMRE rating, and it's actually already been adopted by 90.1. So we as a manufacturer and other manufacturers are printing an ISMRE rating in our submittal packages that are being tested based on calculating your pounds of moisture removed versus your power required to do so. So basically, in this case, dedicated outdoor air is really focused on dehumidifying and taking care of the latent load. So that calculation looks different with the pounds of moisture removed. ISMRE is that integrated seasonal moisture removal efficiency. And again, it's adopted into 90.1, but it is not at this point regulated by the DOE. However, there are some changes coming with ISMRE, and they're actually calling it ISMRE 2. And on the next slide, I have what some of those changes are. But in this case, 90.1 is working on adopting those new changes to ISMRE 2. And kind of in conjunction with that, or simultaneously, the DOE is also working on regulating minimums for ISMRE 2 ratings, similar to how they regulate IEER values for manufacturers as well. So this is obviously a process, so it may be a year or two before you see the DOE actually regulating by the time all of these things become adopted and it become enforced. But it is in the works and is coming. So the changes in ISMRE versus ISMRE 2, if any of you are close to this, these would make a lot of sense. If this is something new to you, obviously these changes are coming and going to affect regulation in the future. Prior to ISMRE 2 coming out, ISMRE was looking at always including reheat, where reheat is no longer required because there are different applications that do and don't require it. ISMRE 2 now doesn't allow you to over dehumidify to take credit for it. What I mean by that is ISMRE is looking at pounds of moisture removed, right? So if we're looking at pounds of moisture removed, someone could try and over dehumidify and get more moisture removal and take credit for that. So that's not going to be allowed in this ISMRE 2. And a couple of other things that just made a lot more sense. External statics were increased depending on airflow for the testing procedure. Changes in the weights of all the points and some of the conditions were changed as well for this ISMRE 2. So again, just some things to note on what's coming from a regulation standpoint for the 100% outside air units and those applications you're applying those to. Another regulation change that is coming in is a refrigeration change, or a refrigerant change. So what has happened recently over I would say the past 6 months to a year is ASHRAE actually worked with California, who is really making the push for a low GWP refrigerant. And there's going to now be a migration to the low GWP refrigerant by 2025 instead of 2023, which was when California was really going to push to enforce it. But now there has really been more of a US stance to push to it by 2025 instead of it just coming from California. So what we're seeing right now from a refrigerant changeover standpoint is many of the compressor manufacturers are working towards their development of their compressors towards the new types of refrigerant. And we're working closely with them on determining which path forward we will be utilizing in our equipment. However, I would say that it is very likely that GreenHack would be going towards the R454B, but we're still working in our R&D with our R&D teams, with our compressor manufacturers to determine that path forward, since now it has moved to 2025. Just a couple notes here. The reason for this change is the maximum will be 750 GWP by 2025. When you look at the difference between the global warming potential, you can see R410A is just over 2,000. The max is going to be 750. And that's where you see the R32 is at 675 and the R454B is 466. So you can see why the push towards that as well. Now, why is R410A really being pushed out of the market? It's because it has high CO2 emissions, that global warming potential, as they call it. If you were to look at a 100-pound tank of R410A, it's basically equivalent to consuming over 10,000 gallons of gasoline. So if you think of a 100-pound tank of R410A releasing the atmosphere, it definitely can play an effect on the global warming potential. So that's why they're looking at that change in the time frame at which you would expect to see it start migrating. And finally, I just wanted to cover a few things of what else is coming from GreenHack. So we have a lot of changes coming in our product line, some of which relates to the DOE efficiencies we just talked about, and new technologies being incorporated into our equipment. So the first one here is we are enhancing our product line to meet those new efficiency ratings and far exceed them, and really make sure that we're in an efficiency rating that provides you with the most benefit, the most cost-effective product, and the most reliable equipment as well. So with our package GX upgrades here, we are going to an inverter compressor as standard. So we will be eliminating digital scrolls from our offering. Standard will be a lead EC condenser fan, which with the option for all EC condenser fans. And we will be providing a single circuit with a single compressor from 5 to 15 tons to meet these higher efficiency metrics. Microchannel coils, which we have been utilizing for a few years now on our product lines, are incorporated into this housing as well. And something to note with microchannel coils, it increases, basically allows you to increase your capacity because of the surface area that those microchannel coils are able to provide. And it also provides a reduction in weight. So we're able to reduce the weight of our equipment as well. So some huge benefits from an efficiency standpoint, reheat capacity out of these units, as well as a weight reduction with this new enhancement to meet these DOE requirements on this particular unit from 5 to 15 tons. In addition to that, we are launching a new product called our RVC, which is going to be a total enthalpy core packaged dedicated outdoor air system unit, and that will be launching in August. So we're a couple months shy of this, but I wanted to give you a preface to this as we are well on the way to having this here in just a few months. The core product is really going to be in complementary to also our RVE product line, which has an energy recovery wheel. So in this case, we'll be utilizing a total enthalpy core, and we will be offering both a fiber membrane and a polymer core option when it comes to this RVC model. And you'll see that below 30 tons. And then above 30 tons, we'll really focus in on utilizing the polymer core technology. So you'll have a couple different options for the core below 30 tons, and then above 30 will be strictly the polymer core option. You can see in the diagram here, this is going to show, two full size cores within, this would be a 5 to 15 ton unit. We will have the option though to do a bypass. So we would introduce an intricate bypass damper into here as well for economizer within this equipment. And then we will offer different frost control sequences. Probably not something you all have to worry about unless you're designing outside of Georgia, where you may be looking at having some sort of timed exhaust or phase and bypass damper to have some options for frost control, or in some cases, an electric preheater as well. So you'll see this new RVC model launch from us from 5 to 70 tons in August. And that will allow you to utilize a total enthalpy core up to 15,000 CFM. So obviously the benefits of the core will allow you to have lower cross leakage. So typically less than 1% cross leakage when it comes to an enthalpy core technology. You'll also still have the benefits of having higher energy efficiency, 50 to 60% total efficiency when it comes to the enthalpy core. Energy wheels are obviously still a lot higher. We'll be offering those in our RVE model that offer the 70 to 80% effectiveness. But something that the market has really utilized, whether it be the cross leakage, looking for an option with a package unit with no moving parts of an energy recovery device, or different applications as well. So something to look forward to us in the coming months. All right, that is the conclusion of all of the updates that I have for you. So hopefully you all gain some knowledge into the changes coming from the DOE and what to expect from manufacturers for different technologies, different system design. Looking at what's coming for DOAS regulations in the future, as well as refrigerant changes, and then the new things coming from GreenHack. So at this point, we can open it up to any questions.